Okay, chapter 26, day 3. We're going to take a look at another chi-squared test today. This chi-squared test is called the chi-squared test for homogeneity. Homogeneous is a term used when things are the same. We're homogeneous. If we are heterogeneous, we would be different. And so we're looking for a test to see if proportions are the same. All right, the biggest thing you have to remember is this is used for multiple populations with one variable. All right. So this is used with multiple populations, one variable. For example, are the proportion of kids that do their homework at freshmen, sophomore, juniors, and seniors the same, or is it different? That's multiple populations. The one variable would be, do they do their homework? All right. The null hypothesis is that the proportions are the same. The alternative is that the proportions are different. All right? Proportions are the same, the proportions are not the same. Really what you're going to do is you're going to take the wording of the question, because they will ask, is there evidence of the following? The null is that the evidence says somehow that they're true, that they are the same proportion, and the alternative is that they're not the same proportion. But you're going to write these in words, really is what happens, okay? Now, the chi-squared value, same degrees, same situation. We have a chi-squared with a degree of freedom. We have O minus E squared divided by E still. But the difference is the data is a two-way table. It has rows and columns, where before our data was just one row of observed data. Now we have two rows, or more than, I should say, we have more than one row and column, all right? We have a two-way table. And that's how you know that it's this type of test. The data is in the two-way table, okay? So, conditions. First of all, again, the data is in counts, and you still have randomization representative sample there, okay? Most of the time you're talking about representative sample. But the data has to be in counts again, the data. We need independence, population greater than 10 times sample, just like before. All expected counts greater than 5. Expected counts greater than 5. Again, what if we don't make it? Well, here's the thing. In this two-way table, if all expected counts are not greater than 5, as long as no more than 20% of those values miss it, you're okay. So no more than 20% can miss, can be under 5. How about that? So if I have a table, let's say 3 by 2, that's going to have 6 boxes in it. If one of the boxes is not greater than 5, I'm okay, because 1 out of 6 is not over 20%. So all expected counts greater than 5. If not, no more than 20% can be under 5. So if not, no more than 20% can be under 5. I meet my conditions. I say it's okay to do a chi-squared test for homogeneity, where yesterday we did goodness of fit. The degrees of freedom, you have to take the number of rows you have minus 1 times the number of columns minus 1. So remember I said I have a 3 by 2. A 3 minus 1 would be 2, a 2 minus 1 would be 1, my degrees of freedom would be 3. Just rows minus 1 times columns minus 1. Expected counts. Before, with goodness of fit, we could take the percentages of what we knew they should be times your sample size to get the expected counts. Here, expected counts are a little bit more difficult. What we have to do is we have to take the total of the row times the total of the column and divide it by the total of the table for each box to get the expected count. All right? You're going to do all of this work on the calculator. Okay? all of the work is done using a matrix on the calculator. You would not want to do all of this by hand. So we're going to take a look at an example in class. You do not have to write this down, but here's an example we're going to look at. Has post-high school choice that graduate makes changed over the decades? Notice, I have post-high school choices. I have different decades, a two-way table. All right? This table has 1, 2, 3, 4 rows, because you never count the total. 4 rows, 3 columns, has 12 boxes in it. All right? So we're going to take a look at this scenario in class, but this type of table is what I'm talking about when I say that it uses a two-way table for the data. Okay? But that's it. We're going to show you how to get it all with the calculator when you get into class.